Well, hi everyone. My name's Ed Tipper from the Department of Earth Sciences here in Cambridge, and it's a pleasure to welcome you to a taster lecture on Earth Sciences. And I thought, what better a taster to possibly give you than to tell you something about Earth's climate story? There is not a day that goes by without climate being in the headlines, but as an Earth scientist, our job is to think about what the science is behind those headlines. And if we look at how temperature has changed over the last 140 years or so on our planet. This is just a little time-lapse animation showing how temperature has changed over the past 140 years, and you'll see the colours get warmer. They go towards more yellow and red colours, in particular in the final 2 decades coming up now. In fact, the last month that has just passed, the month of May, is the warmest May on record, and so that's 140 years of climate records. But as an Earth scientist, we have a much richer record of climate change on a planetary scale, and here we are looking at the past 550 million years of temperature change on our planet. And we've got about 550 million years over here going all the way through to the present day, somewhere over here. We're looking at temperature on the y-axis, where the zero line in here is our baseline reference temperature, which is the last few decades of temperature. So we're looking at how temperature has changed relative to the past few decades, up to about 14 degrees in excess of what we have in the present day. And we're looking at this diagram on 3 different time scales. There are breaks in scale. This is a major break in scale here between 100 million years. So this chunk of the diagram in here is about 400 million years worth of history, believe it or not. This is about 50 million years worth of history. This is about 5 million years worth of history. This is getting on for 1 million years worth of history, and this is the final 20,000 years worth of Earth history. And so we're looking at this on different timescales, but the broad general trend, believe it or not, at least over the past 65 million years, is a trend of a general decrease. But as an Earth scientist, we've got an even longer record of climate on the planet. We know something about our climate about 4.5 billion years ago. And so we've already got ourselves a bit of a problem here. We need to think about geological time. What is 4.5 billion years? That is a very hard thing to wrap our heads around. And well, these little minerals here, this grain here, this blue grain, we're looking at it here under something called cathodoluminescence, but it's a little bit like a microscope view. It's a sophisticated microscope. This sort of length across would be only maybe 100 micrometers or something like that. So it's a very, very tiny grain. It's called the mineral zircon, made of the elements zirconium, silicon, and oxygen. And these minerals are very important because they provide, they're the oldest minerals on the planet, and they provide us with an archive of what was going on. Now, we know their ages, probably based on some science which you already know. So here, this is the geological timescale that we're looking at in millions of years. So this is 4,500 million years ago, going all the way through to the present day. Geologists tend to divide time up into a series of names with unusual names. We don't need to worry about that. The point here is that we know these ages through radioactive decay. Radioactive decay is a very simple thing which you may have come across at school already, or may well come across in your next year of school, where we're just dealing with an exponential decay of a radioactive parent to a stable daughter, more often than not. And we measure these things on mass spectrometers. This image here on the left is one of our mass spectrometers, where we introduce samples at temperatures which are hotter than the sun, which we do in our laboratories. And on the right hand side here, we're looking at the scanning of different ion beams with a very powerful electromagnet, about a half-ton electromagnet, and changing the magnetic field to change the position of ion beams within a mass spectrometer to be able to measure these different isotopes to get the ages of things. But how do we know the climate in the past? Well, for that we look at the chemistry of those minerals zircons that I talked about. And in particular, we look at the chemistry of oxygen in a slightly sophisticated way, where we can interrogate the difference in oxygen isotopes. And oxygen has got 3 different isotopes. Oxygen 16, which is probably the oxygen that you will have heard about the most, which has got 8 protons and 8 neutrons. But there are 2 other isotopes of oxygen. Oxygen 17 with 8 protons and 9 neutrons in its nucleus, and oxygen 18 with 8 protons and 10 neutrons in its nucleus. And when we measure these isotopes of oxygen, in particular the ratio of oxygen 18 to oxygen 16, it provides a fingerprint, a chemical fingerprint or a cryptic fingerprint that tells us that those zircons must have formed from a material where liquid water had been present on the planet. So by looking at the most detailed, oldest chemical fingerprints, we can say that there's been water on the planet by looking at these minerals here. But there are other more simpler ways of figuring out that there was water a long time ago. These particular rocks, or this photograph on the left, is a photograph of a rock from 3.7 billion years ago, and you can see in it, just by looking at the rocks, we can figure out that there must have been liquid water on the planet. All of the components in this rock, and we've got a hammer for scale down here, and all of the components are rounded, and they must have formed in an environment like this river that we have on the right hand side here, a high energy river environment. But this leaves us with a bit of a problem. So we know that there's been liquid water on the planet for almost the entirety of the planetary history. Now, to sustain liquid water, we must have a temperature at the surface of the Earth which is above 0 degrees Celsius, of course, or 273 Kelvin. And we can figure out what the temperature of the Earth should be from a very simple energy balance, which is what this equation represents here, where this is the incoming solar radiation, this is the radius of the planet, A is the distance from the sun, epsilon in here is something called the emissivity, or the radiation leaving the planet. A is something called the albedo, or the reflectivity, something which is known, and sigma down here is a constant which you may have heard of at school called the Boltzmann constant, or the Stefan Boltzmann constant. Now, we can predict what the temperature should be on the planet of the Earth based on knowledge of the solar constant, which astronomers know very well. And they know that the sun was about 30% less luminous 4.5 billion years ago than it is today. And that implies, when we plug the numbers into this equation, that we should have a planetary surface which was frozen. And so something's wrong. And indeed, if we plug the numbers for the present day into this equation, it would imply that the temperature at the surface of the Earth should be about 455 Kelvin, significantly cooler than the planetary average. And of course, the thing that makes up the difference is the greenhouse effect. And so the greenhouse effect we know something about, and what it tells us that in the deep past, because the sun was younger, the greenhouse effect must have been significantly more powerful. And this is a diagram that shows the planetary CO2 emissions in parts per million per volume over planetary history, where this is the beginning of the planet at this point here in time, and we're moving forward to the present day, which is somewhere over here. And this is the planetary history of carbon dioxide emissions from the solid Earth, which is of course where most of the carbon dioxide on the planet comes from. It comes from the solid Earth, degassing from the solid Earth through volcanoes, something like this, to form a greenhouse effect. And this is a photograph that was taken by our former head of department in Iceland. I should say he's not a former head of department because he was taking this picture in a very compromising position. Not at all. He was actually much safer than it looks when this picture was being taken. And so the greenhouse effect, which I'm sure you know something about the greenhouse effect, the science of it. This is just an image taken from the IPCC report on climate change, where we've got an amount of incoming solar radiation. Some of that solar radiation is absorbed by the surface, some is reflected back by the surface. That was that albedo term, which I mentioned very quickly in that energy balance equation. And some energy is reflected back from the planet from clouds. Now, of that energy which is absorbed by the surface, a significant amount gets re-emitted at longer wavelength, but that longer wavelength radiation gets reflected back because of greenhouse gases and comes back as back radiation in all directions, some of it escaping from the clouds. And so that greenhouse effect must have been more intense in the planetary past. And indeed, that greenhouse effect has got us out of a number of very close shaves at a planetary scale. There are times in the early Earth history where we think that the entire planet became a snowball, or the entire planet froze over. And how do we know this? We know it by looking at rocks again, and this is a wonderful photograph where you can see that we've got a rock in here which seems to have deformed a whole load of layers underneath it. And this is effectively what would happen if we drop a rock into some sort of a puddle or something like this with a load of mud, and it would deform the layers underneath. That's exactly what's happening here, and this type of rock is characteristic of rocks which form under glaciers, and they tell us that we must have glaciers present on the planet at this particular time. In fact, we must have had glaciers present on the planet close to the equator, which is perhaps a hard thing to believe. So on long timescales, then, the amount of carbon dioxide being delivered to the planetary surface, to the atmosphere, to the oceans, is being delivered through volcanoes. It's being delivered through volcanic degassing, which is driven by tectonics. So ultimately, the amount of greenhouse gases in the atmosphere are going to be driven by the rate at which plate tectonics proceeds. And so this is just an image showing how plate tectonics have changed over the last 65 million years. The opening of the Atlantic Ocean, for example, in here, and the collision of India into Asia, and the opening up of the Indian Ocean. And so if we try and think about the climate record of that, and we zoom in on that period in here, have a look in this region here. This is the last 65 million years worth of planetary climate history. Well, we're looking at temperature on the y-axis here relative to a stable baseline, which is the present day baseline down here. And over the last 65 million years, there's a very clear trend in climate cooling from a climate maximum up about 55 million years ago down towards the present day. Now, you might ask yourself the question, is that because plate tectonics has slowed down? And if plate tectonics slows down, there'll be less volcanic degassing to the atmosphere? Or is something else going on? And that raises the question, well, where does all the carbon dioxide go? If the solid Earth is emitting carbon dioxide from its planetary interior, where does the carbon dioxide go? And of course it goes into rocks. It gets stored as calcium carbonate in rocks. Here's an example of abundant calcium carbonate forming in the present day, in this case in the Florida Keys, and these beautiful white apparent sands that we've got here. These are not actually grains of sand at all. These are grains of calcium carbonate which are forming, and calcium carbonate, of course, contains carbon dioxide, CaCO3, or another key store of carbon dioxide, or a key remover of carbon dioxide from the atmosphere on long time scales is the formation of coral reefs, for example, something that we will spend a lot of time looking at in detail in the course. This is a microscope view of a specific type of coral, for example. And we figure out how these things work and how these things have worked through geological time. And of course, they form these iconic, if you come from the British Isles, deposits of calcium carbonate, which form the White Cliffs of Dover, for example, or in this case, the White Cliffs seen here near to Durdle Door on the south coast of the United Kingdom, in this case, made out of chalk, which are made out of tiny calcareous fossils, microfossils. And so tectonics has a major influence on climate over geological time, not only through degassing, through volcanic degassing, but also through changing the shape and the depth of ocean basins, because it turns out we can bury far more calcium carbonate as rock in the oceans if seas are shallow, and shallow seas will are determined by plate tectonics, the configuration of plates around the globe. So there's an implicit link between the internal heat engine of the Earth via plate tectonics and the external envelopes of the Earth that we see as climate on the planet. And so I'd like to move further forward with time now into the last 1 million years of climate history, into this period in here. And if we zoom in and look at the last 1 million years of climate history, here we go. And I should say that these are records which are obtained from ice cores, mainly in Antarctica. And these are records which are obtained by drilling the ice and capturing tiny little bubbles of air which have been trapped within that ice. And by looking at the chemistry of that air, we can determine the planetary temperature. And you can see quite clearly that there's a very jagged set of almost sinusoidal variations in climate. This is temperature, remember, on the y-axis over the past 1 million years or so. And what's going on? What's causing those sinusoidal variations? Well, it's mainly changes in astronomical parameters, changes in the Earth's orbit, which influence the amount of solar radiation that's received over time. Firstly, changes in the shape of the ellipse of Earth's orbit around the Sun to a more eccentric ellipse with a regular periodicity between 400 and 100,000 years. The second major factor which will influence the amount of solar radiation received is the obliquity, or the tilt, of Earth's axis as it rotates. It tilts, or the amount of tilt of Earth's axis changes with a periodicity of about 41 kiloyears, changing the amount of solar radiation received. And the final thing that influences the amount of solar radiation received is the precession, how Earth moves around like a spinning top, because Earth, its orbital parameter, it spins like a spinning top and rotates or precesses, and that influences the amount of solar radiation being received, which is quite straightforward to predict the amount of solar radiation being received. And if you stack up those three records, the eccentricity, the obliquity, and the precession, you end up with a solar insolation record that looks remarkably similar to our temperature record that has been discovered through ice cores and through marine sediments further back in time. And then just for the final bit of this taster, just to give you a look at what's going on in the most recent bit of our climate over the last 20,000 years or so. And if we zoom in on that, and in particular what's been going on since the last 10,000 years as we came out of the last deglaciation, and then what's going on in the present day, because it would be impossible not to mention the present day in the context of a talk on Earth's climate history. So here's the last 800,000 years of climate records, mostly from ice core records, as I said earlier. These are these sort of sawtooth sinusoidal curves coming through here, and then this is what's been happening in the last few hundred years. Here's our baseline of carbon dioxide, typical maxima, way less than 300 parts per million by volume, and in the last 200 years or so it has shot up to above 400 parts per million. And indeed, as of yesterday, when I recorded this lecture, the carbon dioxide concentration was all the way up here at about 420 parts per million per volume, showing this annual cyclicity and annual growth over the last 60 years or so. Now, what about the future? Let me try and end on a little bit of optimism. So one of the things we're trying to do, and one of the things that Earth scientists are absolutely implicitly involved in, is trying to get carbon dioxide out of the atmosphere. This is an example from the North Sea, where we've been pumping carbon dioxide into a disused oil well since 1994. And these are seismic reflection surveys showing how that carbon dioxide has accumulated. So this is a little bit like an ultrasound scan, a medical ultrasound scan, but of the Earth, where these bright colours colours show you where the carbon dioxide is accumulating beneath sedimentary layers over time. And this is a time lapse from 1994, 2001, 2004, 2006, 2008. And this is a plan view down here of the carbon dioxide accumulating over time. And in total, we've managed to store about 16 megatons of carbon dioxide in this particular site here, which sounds like a lot, but really it's just a drop in the ocean at the moment. But we're doing lots of other things as well. We're injecting CO2 into the ground and trying to measure the chemistry of the fluids to understand what they tell us, a complex problem of fluid chemistry and multi-phase flow as the carbon dioxide separates from the water. So a rich problem in chemistry, physics, and of course in microbiology, as the reactions which are taking place in the rock are more often than not microbially mediated. And so really, as an earth scientist, we're in a position of information, and we're amongst the best placed people to try and figure out, not only to provide the background of what Earth's climate has been doing in the past so we know what it's going to do in the future, but also to figure out the best mechanisms to start removing carbon dioxide from the atmosphere and put it somewhere safe. And really the future is, to a certain extent, we're there to help inform what's going on. Thanks for your time, and I look forward to perhaps taking some of your questions in the webinar. Thanks very much.